Hello everybody. Today I'm going to introduce the new paper from the Autonomous Vehicle Systems Lab with the title Investigating Driving Interactions, a robust multi-agent simulation framework for autonomous vehicles. The idea is to provide a framework for the testing of new motion planning algorithms that explicitly takes into account realistic driving interactions between road users. With our simulation framework, it's possible to gain deeper insights into the driving behavior of autonomous vehicles, and I'm excited to share our results with you. Let's begin why this novel simulation approach is crucial for the development of autonomous driving software. When driving on public roads, you're seldom alone. Mostly, other road users are in the surrounding of your vehicle, and as a human driver, we have a feeling about what they are going to do. However, for an autonomous vehicle, it's not that easy. Navigating in a complex environment with interacting road users is a very difficult task. If we want to achieve full autonomy on public roads, we must be able to show that the software can handle these environments. This means, for the validation of the driving software, the vehicle must be able to solve these complex scenarios. However, for the statistical evidence of the safety, real-world testing is economically infeasible, since over 1 billion kilometers of driving would be required. Therefore, using a simulation framework helps accelerate the development of autonomous driving, since it allows the fast testing and evaluation of the software. However, the efficiency of a simulation environment is not a matter of chance. First of all, it should be able to simulate a natural driving behavior and consider the influence of interactions between the autonomous vehicle and the surrounding. Most simulation environments consider interactions only to a limited extent. While the agent vehicle can adapt to the surrounding, the behavior of the other vehicles does not necessarily provide a similar responsiveness. However, the mutual influence of driving actions shape the collective behavior of the traffic. Additionally, simulation frameworks should be able to reproduce simulation results and provide measures to compare different planning approaches. To address these necessities, we provide a deterministic multi-agent simulation framework for AVs in fully reactive environments. Our framework synchronously simulates multiple intelligent vehicles. Every vehicle has full decision and driving capabilities. For the comparison of different planning approaches, we provide an interface which allows the easy and efficient integration of individual motion planning algorithms. With that, it is possible to develop new trajectory planning techniques and test and evaluate them in our framework. We provide an open access to the software to the AV community. The module can be downloaded from our GitHub page, and it is fully compatible with the freely available common road scenarios. Of course, there are already a few simulation frameworks which are available for the AV driving software research. Three-dimensional simulation environments such as Carla or CarSim focus on detailed physics and high-quality rendering for realistic motion description and detailed visualization. These frameworks are frequently used to assess the complete software stack, from sensor input to actuator output, and are well suited for evaluating and testing the complete AV functionality. However, generating complex and interactive scenarios is quite effortful. To explicitly tackle the motion planning task without taking into account the overhead of the complete software stack, 2D simulation environments such as NewPlan or ComRoad provide scenarios for benchmarking motion planning algorithms. Here, one can distinguish between recorded datasets from public roads and handcrafted critical edge case scenarios. However, the simulated vehicles do not react on the agent's behavior. In the literature, there are proposals to combine motion planning scenarios with large-scale traffic simulators like Sumo to overcome this shortcoming. Through this, one is able to model fundamental vehicle interactions, but since the simulators use simple rule-based behavior models such as the IDM, no accurate motion description of individual vehicles is possible. There are already a few multi-agent simulations which feature an interactive environment, for example for racing or cooperative planning approaches. However, most simulation environments provide only basic measures to evaluate the planning methods, such as the success or failure rate of the agents, but do not assess the overall criticality due to the agent's decisions. Therefore, we developed an open-source multi-agent simulation framework to test and evaluate different planning algorithms in fully interactive scenarios. So, let's have a look how the simulation environment basically works. It's set up as a synchronous simulation of multiple agents. At the heart of this environment is a global scenario, a comprehensive setting that encapsulates all agents. It's within this scenario that agents navigate and try to reach their final destination. However, it's crucial to note that each agent is confined to a local perspective of the scenario, which only provides a limited view of the environment as the agent perceives it. This means an agent can only consider observations for planning within its visible area. These observations and the prediction of their future behavior are provided to the planning interface of each agent in which the motion planner is embedded. To calculate the predictions, we use a neural network, but it is easily possible to integrate alternative approaches. In each time step, all agents perform one planning step and update their future trajectory simultaneously. The new positions are then aggregated in the global scenario and checked for a collision. Based on the new states, agents update their observations and the procedure repeats. After the simulation is completed, we assess the planned trajectories using our built-in benchmarking and evaluation tool. The agent's performance can be evaluated based on factors such as success rate, collisions, and reaching the goal within a certain time limit. Additionally, we evaluate the criticality of the simulated scenario by calculating metrics such as the headway, time to collision, breakdown number, or encroachment and post-encroachment time at intersections. Now, let's have a look at the simulation of an exemplary intersection with different settings. As planning method, we use our Frenetics motion planner, which is also available on our GitHub page. On the left, we have the deterministic environment where simulated vehicles do not react to the behavior of the autonomous agent, which is the orange vehicle. As we can see, this results in a collision with the vehicle approaching from the top when the agent enters the intersection area and reduces the velocity due to the oncoming traffic. In the middle, we changed the settings such that the green vehicle follows an IDM policy so it can change its velocity but not its driving path. We can see that both vehicles come to a stop at the intersection to avoid the collision. Finally, the green one continues, but the orange car cannot manage to pass the intersection within the time limit. In the final setting on the right, both the green and the orange vehicle are full autonomous vehicles with complete driving decision capabilities. As we can see, after the orange car enters the intersection, the green one bypasses it and makes a little right turn before turning left to avoid the collision. In this scenario, both vehicles successfully managed to cross the intersection. As a second example, we illustrate different behaviors during lane merging. The agent in green tries to merge to the lower lane. As before, three different settings are shown. At the top again a deterministic environment where the blue vehicles on the lower lane follow a recorded trajectory. In the middle, the purple vehicle on the lower lane can change its velocity profile, and in the final setting, the green and the purple vehicle are intelligent agents again. In the first case, the agent collides with the trailing lower vehicle when squeezing in. In the second example, the purple vehicle brakes but doesn't change its path. The collision can be avoided, but when we look at the criticality measures, we can see that a highly critical situation has occurred with a time to collision smaller than half a second. In the final example with two fully autonomous vehicles, one can observe a small evasive maneuver of the purple vehicle to the right. It does not reduce the velocity as much as before, but by making room, the driving corridors overlap less, yielding a higher time to collision and thus a less critical situation. Besides showing the capability of the framework to simulate naturalistic driving behavior, it's crucial to consider the runtime of simulations for a fast and efficient driving software development. This slide shows a runtime analysis with increasing number of simulated agents. The simulation is conducted in two configurations. First as a single-core program, and second as a multi-core program with up to 8 cores, where batches of agents are distributed among the processors. When using only one core, the average computation time rises remarkably as the number of agents increases, while distributed computation accelerates the calculation and reduces the average computation time of a single planning cycle by up to 74%. However, irrespective of the number of agents, the framework's computation time per time step exceeds the simulated discretized time step size of 0.1 seconds. Thus, with the framework, we cannot achieve real-time simulations, even when a planning method capable of real-time calculations is used. While hindering real-time performance, the synchronous nature of the simulation framework ensures the determinism and reproducibility of experiments, which is one of the main goals of our framework. As we reach the end of the presentation, we do a short recap of what the multi-agent simulation framework is all about, and what the next steps might be to improve our framework. First of all, it is designed for the development, testing, and evaluation of non-cooperative interactive driving of AVs in complex environments, where several agents simultaneously navigate to individual destinations. Through the synchronous planning, we ensure determinism and reproducibility of experiments, but we cannot attain real-time simulations. Finally, the experiments we conducted highlight the impact of vehicle interactions on trajectory planning methods for autonomous driving and emphasize the importance of simulation frameworks which are able to simulate realistic driving. Currently, all agents use the same planning approach. The experiment variability could be further increased by integrating different planning methods for different agents. Additionally, we see potential for the efficient exploration of cooperative behavior and inter-vehicle communication, which could easily be included in our framework, and it could benefit the training of multi-agent reinforcement learning-based trajectory planning methods. As we conclude, I'd like to thank you all for your attention. And for those of you who are interested in exploring more details, we have provided QR codes which directly link to the paper, the GitHub repository for the simulation framework, and our lab website for more information about ongoing research projects. We are excited to share our work with the community and welcome any collaborations or discussions. Once again, thank you for joining the presentation of the Autonomous Vehicle Systems Lab today.